Assalamualaikum warahmatullahi wabarakatuh. This is our project for System Dynamic and Control Engineering subject. Our project title is a closed loop speed control of a DC motor. We are from Group 8. Our members are Ashif Alash, Nur Shahira, Aida Najeha, Ahmad Zaim, which is me, and Nur Hidayah. Assalamualaikum. My name is Ahmad Zaim bin Ahmad Zakri with matriculation number A164975. For today, I'm going to talk a little bit about introduction to our project. A DC motor is any of a class of rotary electrical motors that convert direct current of electrical energy into mechanical energy. There are two basic of closed loop control system, which is open loop control and closed loop control. Open loop control, which is no feedback loop, is employed, while closed loop control is utilize feedback to measure the actual system operating parameter being controlled. The tachometer also provides a feedback voltage which is proportional to the actual motor speed. Next, we go to the objective of our project. First, to identify the system in open loop in order to construct the best corrector, which make it possible to regulate the rotation speed of the motor in the closed loop system. Second, to regulate the angular velocity of the motor such that it remains constant despite the presence of unmodeled dynamics such as noise and perturbation. Next, we go to problem statement of our project. First, how the Simulink function to evaluate value of input voltage with speed of 25 rad per second. Second, how the proportional gain overcomes the position error. Does it affect the stability of the system?
Hi, my name is Nur Hidayah binti Mat Hashim and I will explain about the methodology of this project. This is our instrument of the project, which is have 6 apparatus to accomplish this laboratory project, which is DC electric motor, tacho generator, oscilloscope, breadboard, a steel disc, and a controller. Next, the step required for model L1, section 2, which is tachometer calibration. First of all, we need to insert the value of the voltage supply, which is 15 volt, into the Simulink. Then we sub in the value of the tachometer reading in radian per second and deduce the value of kT by using this formula. After that, we get the result. From the result, we can get the value of the voltage when motor speed is achieved 25 radian per second. Then this is step required for section 3, which is modeling of a DC motor. First of all, we need to insert the value of the voltage supply, which is 168.4 volt, into the Simulink. Then we obtain the value of time constant, settling time based on the graph that appear in the oscilloscope, and sub into the formula to get the value of GS by using this formula. Then, if the system is in the first order, the static gain and time constant of the DC motor will deduce by using this formula. After that, transfer function of the output speed of the motor is deduced. Then, the temporal equation of the motor can obtain by using Laplace inverse. Last but not least, the value of the steady state speed of the motor was calculated when condition the time is equivalent with time constant.
Assalamualaikum warahmatullahi wabarakatuh. My name is Ashif Halash bin Abdul Majid with the matrix numbers of A163763. So today I will explain to you guys the methodology and the results for model L2 and LTB. For the methodology of the L2, the first step is we will insert the value of voltage, which is the 3 volt, to have the 750 revolution per minute as the reference point signal and the tachometer output feedback to build the closed systems. And then the value of the 4 resistance was determined in order to have the voltage error equals to voltage input minus the voltage output using the formula that is given. After that, we enter the value in the Simulink model, and from the error graph we can calculate the actual percentage error of the system using the formula of V input minus V output over V input times by 100%. And then lastly, a closed loop system is built to gain the value of Kp such that the steady state error is minimized to less than 5% and the value of the proportional gain is calculated. For the methodology of the L3B. So the first step is the value of the proportional gain Kp is calculated using the formula given. As you can see, there is an unknown which is the Gs and the Hs. The value of the Gs and the Hs was calculated from the L1. And then the value of the R5 is fixed at 10k ohm. Then the value of RV can be found out using the below formula, which is the Kp equals to 1 plus RV over R5. And then the system is then determined whether it is correctly regulated by turning off the electromagnetic system.
Alright, for section 2, we have given range voltage supply 0 until 15 volt. So we have put in the value of voltage supply, which is 15 volt, into the Simulink. After we run Simulink, we get the tachometer reading, which is 2.227 radian per second. After get the result from the simulation, we will use the equation given from the project brief, which is V equal to kT times angular velocity. Then we will get the value kT equal to 6.7355. So to get value of the voltage for steady state speed, 25 radian per second will be multiplied by 6.7355, get 168.4 volt. Then we run again the Simulink with insert the value of 168.4 volt as a voltage input. After that, we know that 168.4 volt is the voltage value needed to get the steady state speed, 25 radian per second. As we can see, the voltmeter reading is 2.05 volt. 2.05 volt is a value of a voltage output. This slide shows that the graph voltage over time. We get the graph from the oscilloscope result. Then we will find the value of KDC based on the graph given. So the value voltage output 2.05 volt will be multiplied by constant value of 0.63. And we get the value of y-axis, which is 1.2925 volt. From the graph, we will get the value of time constant 0.21 second, which is intersect with 1.2915 volt. Then substitute the value of the time constant in A formula to get the value of A. Based on formula given in project brief, Vt equal to K over A, we will use this formula to find the value of the KDC, which is 9.762. After that, we need to deduce the transfer function of the output speed of the motor by using the formula first order control system. Then, unit step signal for Rs is equal to 1 over S will be multiplied by Gs to get the equation of output control system, Cs. Alright, as we have learned before, we will use the partial fraction to get the value of A and B. The value of A is equal to 1 while B is equal to -1. So, we can do the inverse Laplace transform to get the equation of Ct. The value of time is equivalent with time constant at steady state speed of the motor. Then the value of Ct was calculated.
For the results of the L2, as you can see below is the Simulink model for the L2. From this model, you can actually get the value of the voltage error, the value of the actual angular velocity time response, and the value of voltage output. We just need to change the value of the voltage input, the value of the resistance, and the value of the resistance at the proportional controller gain to get the value that's what we needed. So the first thing that we're going to do is we are going to insert the value of the voltage input, which is the 168.39 volt in the Simulink model. And then we will get the feedback voltage, which is the Vt equals to 4.002 volt, and the voltage error is equal to 164.4 volts. And then by using the formula given, we will equal it to 1, and then we will get the value of the resistance of R1, R2, R3, and R4 is equals to 1000. Next, we will calculate the actual percentage error. By using the formula given, we will get that the percentage error is 2.375%. After that, we will create a loop system and make a transfer function of the loop system by using the formula of transfer function equals to kpgs over 1 plus hsgs kp by transfer function. And then, to find the root locus analysis, we will use the MATLAB system. We just need to insert the commands needed to show the graph, and then the graph will show that there is only the negative real roots based on the graph. To find a suitable value for Kp, we will use the value of the steady state error is equal to 5%, which is the 0.05 as the reference. And then we will get that the value of Kp is equals to 110.92. Then we will find the value of Rv at fixed value of R5 equals to 10 k ohms by using the formula of Kp equals to 1 plus Rv over R5, and we will get that the value of Rv is equals to 1099.2 k ohms. After that, we will substitute the value of Rv inside the L2 model, and we will get the value of the graph of actual angular velocity time response. From the graph, you can read that the value of the actual angular velocity is equals to 1180.70 radian per second. And then, for the model L3b, you can see that the Simulink model of L3b is actually equals to L2, but they just add the disturbance to compare the value of the disturbance and the value of the L2 where there is no disturbance. So from the effect of the disturbance of t larger than 5 seconds, the value of the angular velocity changed to 1180.56 radian per second. It shows that the disturbance reduced the value of the angular velocity by 0.14 radian per second.
Discussion for test 1. Tachometer calibration. This operation is very simple when an input signal directs the control element to the response so that the output will be produced. In order to achieve 25 radians per second for the speed, the equation has been used to determine the velocity input, which is in result we get the Vin is 168.39 volt. Modeling of a DC motor. This experiment is in first order system, which we can determine through the graph that we can get from the oscilloscope, or voltage versus time. Since the most basic requirement of a motor that it should rotate at desired speed, so that we require that the steady state error of motor speed should be plus minus 20%. Another performance requirement for our motor that it must accelerate to its steady state speed as soon as it turns on, so that we need to have a certain time and the value that can determine to the graph that we can get from the oscilloscope just now. Since a speed faster than the reference may damage the equipment, we need to have a step response with overshoot less than 45%. To accomplish all these requirements, we need to deduce the transfer function of the output speed of the motor, which is we get the result is velocity out equal to 2.05 volt. After that, the Laplace inverse transform need to be done to get the temporal equation of the motor speed. Lastly, the value of the steady state speed can be calculated when time is equivalent to the time constant. In Lab 3A, it shows that decreasing in the speed that might subjected to the disturbance due to the friction torque and Coggin torque. Discussion for test 2. By using the given input voltage is equal to 3 volt, we need to build the system and get the actually percentage error from the system by using formula, which in result we get 97.62%. Root locus have been created by using MATLAB command in order to get 5% error. Based on the error graph, we can see a decreasing curve graph and a constant value of 2.34 volt. And for the oscilloscope graph, it shows the increasing curve graph and stay constant at 0.67 volt. For lab 3B, the result shows decreasing value of angular velocity due to disturbance. There might be some error while making and calculating during the calculation that might affect the result. From experiment, we can see the difference between the open loop and the closed loop control system. For the open loop that has been conducted in the lab 1, it shows an open loop action, which is a control chain. It also can counteract against disturbance for which it has been designed. Lab 3A has been done to determine this disturbance. It also cannot become unstable as long as the control object is stable. For the closed loop, that has been done in the lab 2, it shows a closed loop action which in a closed control loop. It also can counteract against disturbance, which conduct this experiment in lab 3B by input the required resistance value. It also can become unstable if the control variable does not fade away but grows theoretically to an infinite value. Lastly, there might be some unexpected error occurs when examining and handling this experiment. For the lab 1, this error is due to inserting random value for the input voltage, thus the result shows inaccurate. There will also not have any feedback to the controller that indicates the change in the speed. So in order to get the better end result, our team changed the voltage input that can satisfy 25 radian per second so that the error will be zero. Furthermore, runtime error usually occur when running and executing the program or software. Runtime error can occur either in hardware or software, causing it to malfunction. Software runtime error also can occur in arithmetic exception, which include control and data flow related defects such as non-initialized variable, pointers, and etc.
Finally, we have reached our last subtopic for this project, which is conclusion. With steady state error of 20%, to achieve steady state angular velocity of 25 rad per second, we need 168.4 volt as an input voltage to the system to get the desired value of the angular velocity. Next, maximum overshoot hit the desired value, which is below 45% as the system in a first order system. That's all from us. Thank you.